Now let's work an example of a binomial probability distribution where we create the probability distribution and then use it to answer some questions. So here's the example. According to Air Travel Magazine, the 5 largest airlines had an on-time percentage of 84.7% in November 2010. Suppose that 4 flights are randomly selected from November 2010 and the number of on-time flights, X, is recorded. Construct a probability distribution for the random variable X. So let's note what information we're given about our binomial probability distribution. All right, so we know that our procedure will have n equals 4 trials. We'll have 4 trials in our procedure. We know that the probability of success, P, is, well, let's do it. We'll write it, probability of success, which is P, lowercase p, is equal to this 84.7%, or as a decimal, 0.847. Okay, so with that probability, this is a fixed probability of success. Success we're going to count as an on-time flight. We have a fixed probability that will stay constant through all the trials. We have a fixed number of trials, 4, and we have outcomes in 2 categories. The flight is either on time or it is not. So the last question then for our requirements is, are our trials independent? In other words, are we going to sample with replacement or without replacement, or can we use the rule, the 5% rule? Well, we don't really know how many flights there were in November 2010, but if we say that there were and this is the case, somewhere between 2,000 and 3,500 per day, and our sample size is just 4, then we can pretty much accept, and without calculating, that our n is less than or equal to 0.05 times the population, because we're talking about the whole month of November, so 30 days times, say 2,500 flights a day, and we're just going to look at 4, okay, for these 5 largest airlines. So I would say we can assume independence. So I'm just going to write that note. We may assume independence. Since 4 is going to be much less than the population, than 0.05 n, without even calculating that number. 30 times 2,500, very large number. Okay, so now we're good to go on creating our probability distribution. We'll just need this information to do it. So let's set up a table over here where we have our random variable x, and we're going to generate the probability for each value of the random variable. That's what a probability distribution is. It's a table or a formula that, or a graph that shows us for each value of the random variable its probability. So what are the possible values of our random variable? Well, we could have 0 of the 4 flights on time. We could have 1, 2, 3, or 4. And that's it. Those are all the possible values of the random variable when 4 is the number of trials. Okay, to calculate, we're going to use the technology method of calculating. So let's pull up the TI-84, see if we can make sure we can see that. There we go. We'll find our binomial probability distributions here on the distribution key. It's a blue function key. Oops, second. There we go. Okay, and so we can tab down till we find Binomial PDF, probability density function, and that's the one we want. Enter. Now this calculator actually asks you the number of trials, what is your probability of success, and what is your X value. So in our case, we're going to start with our first probability where X is 0. The number of trials will be 4. Enter. The probability was 0.847. Enter. And we're interested in 0. Enter. So if you don't have a calculator that lists it as number of trials, probability, and X value, then this is the order that you would put in those parentheses that it gave you. N, P, and X. It's always in that order with a comma between, okay? And the comma is just above the 7 key. So N, P, X. Okay, enter. Now there's our probability. Now probabilities aren't greater than 1, so when you see a probability like that, you should stop and think, wait a minute, what am I seeing? And notice the E and the -4. This is scientific notation. It's telling us that we need to multiply this 5.4798 times 10 to the -4. Or in other words, move the decimal 4 places to the left. So when I do that, we get get that again, 0.0005. Okay, pull that back up. All right. So be careful with that. Don't just write down 5.47. In your mind, you should immediately think there's no such thing as a probability greater than 1, right? So that'll tell you, look to see if perhaps you're getting a value in scientific notation or perhaps something else has gone wrong. Alright, so that was for 0. Now let's do the same thing again. We want to go to our distribution function. And go down to the binomial probability density function. And our number of trials is still 4. So I'll enter that. Our probability of success is constant, but this time my random variable X I'm interested in is 1. Okay, enter. Enter. Alright, and now it's ready. You see NPX with commas between. Enter. And this time I get 0.0121. Okay? So we'll do that for 2, 3, and 4. I'll go a little bit faster. This time I know that it's function A on here, so I could also, whoops, this is very sensitive. I could also use the alpha key and tap A, and it took me straight down to it. So if you have that option on your calculator, you might try that. Alright, so 4 hasn't changed, my probability doesn't change, but now I'm interested in 2. Enter, enter, and NPX. Enter, and this time I get 0.1008. 0.1, I'm rounding there to 4 decimal places, and let's see what we have now. Do this again for 3. Again, I'm going to use my shortcut, alpha A. Trials is the same. Enter, enter. Value now is 3. Enter, enter. NPX. Enter 0.3719. And one more time. Second key, distributions, alpha A, enter, enter, and now we want 4. Enter, enter, NPX. I keep saying that. That's really important for those of you that don't have the number of trials broken out where they ask it for that way, because you can see it has to go in that way in the parentheses. So that's very important to know it's NPX. This time we get 0.5147. Okay, and I actually wanted to round these to 3, so I'm going to come back up here and write this one as 0.001, 0.012, whoops, 0.101, 0.372, and 0.515. And recall that if it's a probability distribution, the sum of the probabilities must equal 1. So 1 plus 2 is 3, plus 1 is 4, plus 2 is 6, plus 5 is 11. And now I have 1 and 1, 2, 9, plus 2 plus 7 is 9, 10. And 1 and 1 is 2, plus 3 is 5, plus 5 is 10. And we said we might be off slightly due to rounding. You saw I was rounding to get these 4, then I rounded again to get here, so I am off by a little bit, but that's a very small amount, and that will happen, so we just need to be prepared for that. Okay, so again, what we used to get these was the binomial probability density function, and the order we put that data in is NPX. We used the technology. We could not have used the tables because the tables don't have this probability, 84.7%. It's just selected probabilities in the tables, and that's not one of them. But we could have used the formula to do it, and we would have gotten the same results because this is exactly what your calculator is doing. Okay, given this information, now we can answer some questions. The first question is, what's the probability that at least one flight will be on time? Okay, the probability that at least one. Now we've got to get used to this wording. Probability of at least one. Well, hopefully you remember when we saw that before. At least one. The least possible number is 1. That means 1 or 2 or 3 or 4, right? In other words, everything but none. So we need to, it's very important to learn this, that this is the same, it's that we use complements, the same as 1 minus the probability of none. So 1 minus the probability of 0. 1 minus 0 was, we'll use our rounded to 3 decimal place result, 0, 0, 1. And we get the result 0.999. So there's a really good chance at least one of these 4 will be on time. Okay, let's look at another question we could answer with this data. What's the probability that at most one flight will be on time? Well, let's think about what they're asking us there. At most one. Here are our choices: 0, 1, 2, 3, or 4. So when we say at most one, this is what we're talking about. The most it could be. Now it could be 0 or it could be 1, but the most it could be is 1. So let me write that. Probability of at most 1. Well, that's equal to the probability of 1 or 0, which I could write as the probability of 1. Remember, or means add, or 0. Okay, and we have these numbers in our table. 0.001 was the probability of 0. We just used that one. The probability of 1 is 0.012. Okay, and when we add these together, we get 0.013. Now, using the table, that's real easy to do. We just came up here and said if the most possible number is 1, then we're talking about these two right here. Add them together. Okay, We could also get that using the technology directly. Another way to look at most 1 is the probability that x is less than or equal to 1, right? The most it could be is 1, so it's a number that's less than or equal to 1. So what we can do is use the binomial, and instead of the PDF we have a cumulative density function on the calculator, and we'll put in n and p and x, and what this does is it's cumulative. So if I put in a 1, it's going to give me the probabilities of all the values up to 1, 0 and 1. Now if I wanted x is less than 7, it would actually give me the probabilities, the sum of the probabilities from 0 to 7. So that's what the cumulative function will do for us. Okay, so let's use technology and see if we get this same answer. All right, go to our distributions. This time, tab down. We saw the PDF, right below it is the cumulative density function. Okay, so that's what we want. Enter. And now again it asks me my trials. 4. Enter. P-value is 0.847. Enter. And now my x value is 1. But because I'm using the cumulative density function, it's going to give me everything up to and including 1. Enter, and here we get 0.01268. Let's pull that back up. 0.01268, yes. Okay. Which is approximately equal to 0.013, which is what we found here. Same thing. So that cumulative density function can help us if this is what we're looking for. Okay, third question we can look at. What is the probability that more than one flight will be on time? So how is that written? Again, let's look at our choices. All right, the probability of more than one. So we're talking about these. So we want the probability more than one. That's the probability of 2 or 3 or 4, which or means add. So we've got the probability of 2 plus probability of 3 plus the probability of 4. And using our table, we can get that answer. The probability of 2, let's see, in our table, 2 is 0.101. 0.101 plus 3, 0.372 plus 4, 0.515. And we add those together and we get 0.988. So the probability that more than one flight will be on time is 0.988. Okay. So more than one and at most one are complements, so another way we could do that is to say 1 minus the probability of at most 1, because remember that was 0 and 1. This is 2, 3, and 4. And what did we get for at most 1? We got, there it is, 0.013, and here we get 0.987. Now they're not exactly the same off in the thousandths place, however, that's just a rounding difference. Okay, let's go on to the next part then. Would it be unusual for less than 2 flights to be on time. So we'll use unusual, U-N-U-S-U, that's a U-A-L. Unusual is going to be any probability that's less than or equal to 0.05. Okay? We'll use that as our guide for unusual probability. So the probability of less than 2. Well, less than 2, what values are less than 2? 1 or 0. So we already saw that in part B, right? That was at most 1. So this is just another way to say that, and that was 0.013. And since 0.013 is less than 0.05, it would be unusual. For less than 2 flights to be on time.